Here we are, lecture 23, example 1. Of course, there's no lecture for this, but decent example. So the second example problem is a programming problem, but our first one is going to be a RISC-V hardware modification program. So once again, I love these type of problems because they indicate that you know what's going on to the point of being able to change the hardware. Now, it'd be great if you're a programmer, but this is partially a hardware class, and you both need to program and need to understand the underlying hardware. So these two instructions are branch if bit set or branch if bit cleared. So currently we have like 6 branch instructions, 6 base branch instructions that look a lot like this. They like BEQ, etc., etc. So it looks like we could probably use the same type of instruction. So what it's doing here, it's saying if the bit in RS1 given by the value of RS2 is equal to 1, then it takes the branch. Otherwise, it doesn't take the branch. And so this is going to be, if you look at this, this is very similar to maybe the shifting that we did in the ALU. So this is going to be, I'm going to try to write some Verilog here. If RS1 of RS2 4 down to 0 equal 1. Okay, and that's going to blah, blah, blah. That's what I'm looking for. And if that's for this one right here, I can do the same thing for that one if that bit equals 0. So it's fairly simple Verilog code to get these things working. So it's not a big deal. So let's see how to do this. And once again, I'm going to talk these through, and the solution is in the book somewhere. It's in chapter 20 or 19. I forgot what chapter it is. So let's describe first I'll go through this list to describe the changes we need to make to the hardware. So let's, anytime we're doing this, we want to keep it as minimum as possible. So I'm getting out my picture here. I'm actually not getting out the picture. I'm suspecting that we can fit this in to the existing branch instructions. So these are the existing branch instructions. If you look at them, there's 6 of them, and they're differentiated by these func3 codes. So this is the func3 opcode line. So there's 6 of them. We are going to add 2 instructions, so that's going to fit. So these 2 new instructions are simply going to have a different func3 code, but for by all means, we're going to use the same 7-bit opcode for these simply because we can. We have space for it. That's what we're going to do. Okay, so that's one problem solved. These are going to be a B-type instruction, and so we can adopt those opcode, give it a different func3 code. Life is good on that one. And so what else do we need to do here is, now we're at the hardware diagram. So everything, it's a branch type instruction. So if you remember, everything having to do with a branch is calculated inside this thing. And so what we're interested in is the 2 registers. They're already there. What we want is, these are just like comparator type things. What we want is another signal coming in here to say, I know, I'll say bit set or bit cleared. Okay, so what we're going to do is take this module here, add some more hardware to it, and add a output to it, whether the bit set or the bit is cleared. Put that in the decoder, the control unit decoder. That's going to allow the decoder decide whether it needs to branch or not. Now, these are branch instructions, meaning it either takes the branch or goes on to the next instruction. And the way it takes that branch is a combination of the PC write and the PC source. So we have all the functionality there already. What we need to do is add the functionality in here to recognize the instruction. Opcode's the same, but we need to make it recognize those new func3 codes, which is another part of the opcode. So this this needs some extra hardware in it to see whether the bit is set. This is just it's gonna give the control unit decoder a signal saying, hey, it's set or not set, take the jump or not, if we indeed are executing one of these instructions. And that's most of it right there. Now, well, the issue here is we since it is a branch type instruction, we don't need to change the state machine in any way, because we're reusing so much of the other instruction. And so what else here? Do we need to change anything else on this one? I don't think so. Everything is set up to work as is. So we're going to call that first bullet done. So the changes to the assembler are, I have to tell the assembler that I've added 2 new instructions. It has to recognize those instructions and send out, the correct opcodes, etc., etc. They are B-type instructions. It has to recognize the. So we're not going to. It's because they're B-type instructions. Because it fit, we don't need to change the 7-bit opcode. We do need to change or to add 2 new Func3 codes. So we didn't. We didn't add. We changed a couple modules, which is the decoder and the branch. What is the branch address generator? Branch condition generator. Those are combinatorial modules, so that didn't change memory. We didn't change the reg file. We didn't change the program counter. We didn't change main memory. We didn't add any states to it. Which remember, there's the state machine has storage in it because it's a state machine that has state. And so we didn't change any of that stuff, so there are going to be no modifications to memory. Quite a useful instruction, because it's going to save me a bunch of masking and possibly shifting around. Not a big deal, but the masking typically is going to use up registers. Here, this implements it automatically, and it saves a couple instructions. So typically, I would put this in my computer if I had a whole bunch of control operations based on a bit. So whether a bit is set or a bit is cleared, if I had a whole bunch of those, I would certainly use this instruction. Now typically for microcontrollers, they're controllers, right? They're controlling something, and they control things by reading the status of a bit and writing some output based on the status of that. So that would be typically, this would be a very, very helpful instruction. And I didn't make this up. I know there are architectures out there that have instructions like this. So heck, if certainly RISC-V doesn't have it, but RISC-V has the ability to create this functionality. It just takes extra instructions. So if we actually put this in our computer, it would be running faster. And that's all I had for this one.